For our second example here, we have the following statement. Use cylindrical shells to find the volume of the solid obtained by rotating the region bound by the curves x equals 2y squared, where y is strictly greater than or equal to 0, x equals 2, and we're going to rotate that region about the line y equals 2. So let's graph this sucker. If you're a little intimidated by that first curve, then just play a little bit of make-believe, dude. What do I mean? Let's pretend that this is y equals 2x squared. Could you graph that? That's a parabola that's a little bit skinnier than normal, twice as tall, but this is the same thing, but it's going to be on its side. So our first curve looks something like this. We want x equals 2. I'll just put that out here somewhere. X equals 2. This is x equals 2y squared. And then we're specifically told that we just want y to be greater than or equal to 0. So let's see. It'll just be that region there only. So let me erase some of this. There we go. And then we're going to rotate about the line y equals 2, which is up here somewhere. Let's see. We should find those points of intersection, I suppose. This is 0, 0. Where do these two intersect? Well, if I set the two curves equal to each other, that is x equals 2y squared is equal to 2, then y squared is equal to 1, or y equals plus or minus 1. So this must be the point 2 comma positive 1, since it's up above the x-axis. Okay, so much funsies. And I guess if you wanted, this is 2, 0. There's our region. We're going to rotate that around the line y equals 2. I'll just put an arbitrary line up there, y equals 2. And we're going to rotate about this line. So we're supposed to use cylindrical shells. So what I'm going to do is, around my axis of rotation, I'm going to draw a little cylindrical shell just to get oriented here. That wasn't so hard. There's my little shell. And the wall thickness is going to be a small dy here. So we're going to have shells dy, like so much funsies. So I'll start with that general form. Shells dy is going to be the integral from y equals a to y equals b, or y equals c to y equals d. Doesn't really matter. 2 pi radius times the height integrated dy. So let's talk about what these features are. This is the integral. In terms of my horizontal strip, we should draw that in there. Let's see. If this is my horizontal approximating strip, it's going to run through my region like this. And the lowest one is going to occur down here when y is equal to 0. And as it goes up here and runs through this region, the highest one is going to appear at y equals 1. So this is going to go from y equals 0 to y equals 1, 2 pi. We need to figure out what the radius is. We need to figure out what the height is. And then we'll integrate that sucker dy. So let's talk about the radius. This one is maybe a little bit trickier. Remember that the radius is measured from the axis of rotation over to our approximating strip. Now normally this is going to be a height of 2, or y equals 2, and this arbitrary distance, what do you have to go on? The arbitrary distance down here from the x-axis up to a point on that red line is just going to be y. So this must be 2 minus y, or again, top minus bottom. See how that works? Top minus bottom there. Once you get the hang of top minus bottom, or left versus right, and know how to identify it, these problems become a lot less cryptic. So really focus on identifying top versus bottom or right minus left, as we're going to do in our height here. Because our shell is kind of on its side here, this length is our height. Now again, if we just calmly think about this as being the right side of that red strip versus the left side of that red strip, what do we have? Well, the right side occurs at x equals 2. The left side occurs on this curve. And if this little arbitrary distance here is x, that's also equal to 2y squared. So this is the left side is the curve. So right minus left is going to be 2 minus 2y squared. And that becomes pretty straightforward. So let's integrate this sucker. There's our setup. If you want to stare at it for a second, go ahead. But it's best you go through that construction again on your own from start to finish. This was the work, by the way. This was all of the real work. Everything else is just the funsies part. So it's a little hard for students to stare at that and go, oh, yeah, obviously. You don't want to stare at that. You want to start with a blank page, you want to draw it yourself, and you want to go through the construction and the measurements by yourself, man. You're the engineer. Get the ruler out and measure that stuff, man. Okay, so we'll factor out, what can we factor out? Let's see. I can even factor out a 2 here, maybe. So let's factor out that 2 and that 2 pi and make this 4 pi times the integral from 0 to 1 of 2 minus y times 1 minus y squared dy. We'll FOIL that out, and this will be 4 pi times the integral from 0 to 1 of 2 minus 2y squared minus y plus y cubed integrated dy. And that'll be 4 pi times the antiderivative, 2y minus 2/3 y cubed minus 1/2 y squared plus 1/4 y to the 4th integrated between 0 and 1, which will leave us with the following hot mess. 2 minus 2/3 minus 1/2 plus 1/4 minus 0 when we plug in 0. And arithmetic, dude. Let's see, 4 pi, and this will all be over a common denominator of 12. And that'll be 24 twelfths minus 8 twelfths minus 6 twelfths plus 3 twelfths. And we'll clean that up, and 4 will go into 12 3 times. And 8 and 6 is 14. 24 minus 16, sorry, 24 minus 14 is 10, plus 3 more is 13. Pi over 3, he wheezed. Something like that. Again, I'm not perfect. I could make a small arithmetic error in there. So, again, if you guys find any errors, let me know, and I'll try to go back and edit these videos. The setup is solid, though, man. Nailed it. Okay. See you next time.